we already seen one type of fluid, Newtonian fluid, right? So what does it Newtonian fluid means? Tau is equal to mu into du by dy. So this is Newton's law of viscosity, and if the fluid follow this law, then I will call that fluid to be Newtonian fluid. So the fluid which is going to follow this law, that is the shear stress is equal to viscosity into velocity gradient, I will be calling that as to be Newtonian fluid. Now all the other fluid which is not going to come under Newtonian fluid, that is if it is not going to follow Newton's law of viscosity, then I will call that fluid as non-Newtonian fluid. So if the fluid is not following Newtonian's law, then I will call that fluid to be non-Newtonian fluid. So in case of Newtonian fluid, we see in different formulas and different characteristics like viscosity, etc, etc. But now for non-Newtonian fluid, like how to define it. For example, here this is shear stress is equal to mu into du by dy. I can directly find shear stress for any Newtonian fluid. But if it is non-Newtonian fluid, first thing is I need to define that non-Newtonian fluid, right? For that I need some formula for the shear stress, same way. So first we have one generalized formula, general formula for tau. This general formula for tau is applicable for all type of fluid with some conditions. Let me first write you that formula, then you will understand. Tau is equal to A into du by dy whole power n plus b. So this is the generalized formula where A, n and b all three are constant. Meaning of A, n and b you will get to know it once we discuss about different types of fluids. Now for Newtonian fluid, how can I say? For Newtonian fluid, this is my generalized equation, right? For Newtonian fluid, I know that Newtonian fluid follows Newton's law of viscosity, which is nothing but tau is equal to mu into du by dy, right? So this is general equation, and Newton fluid follows this equation. Then by comparing these two, I can easily say for Newtonian fluid, A is nothing but mu and n is nothing but 1, right? If I compare these two, A is nothing but mu and n is nothing but 1 and b is nothing but 0, right? So if these conditions are satisfied, then it is Newtonian fluid. Now you can easily guess, if I substitute in place of A, if I substitute mu, and if I substitute 1 and if I substitute b is equal to 0, then tau will bring me direct Newton's law of viscosity itself, okay? So this is Newton's fluid, Newtonian fluid. Now we will classify non-Newtonian fluid based on this A value, n value and b value. So I am going to classify different types of fluid by using the help of our generalized equation, okay? So first let me start with the first non-Newtonian fluid, which is dilatant fluid. So in case of dilatant fluid, the b value will be 0 and n will be greater than 1. So this is the condition. So n value will be greater than 1 and b value will be equals to 0. So tau, I know the generalized equation, tau is equal to A into du by dy whole power n plus b, right? Now for a dilatant fluid, b value should be 0 and n value should be greater than 1. So this is for dilatant fluid, and now recollect it for Newtonian fluid. For Newtonian fluid, I know that tau is equal to mu into du by dy, right? For Newtonian fluid, tau is equal to mu into du by dy. If I want to write this equation in terms of that, okay, if I want to write this equation in terms of that, what I can do? In terms of that means what? Here for Newtonian fluid, I taken tau in y-axis and du by dy in x-axis, and I drawn the curve like this. This we know very clearly because y and this is x. Y is equal to mx. Straight line equation form we already discussed in the last video, okay, in the previous videos. Now tau is in y-axis and du by dy is in x-axis, and it is varying linearly. Tau is varying linearly with respect to du by dy, okay, or rate of shear strain. Either rate of shear strain or velocity gradient, both are same. That is also we already discussed. Now In this case, I want to write tau in y-axis and du by dy in x-axis. So in that case, in same manner, I need to resolve this. So what can I do? Tau is equal to a. I can write this du by dy whole power n like this, du by dy whole power n minus 1 into du by dy whole power 1. I can write like this, right? So du by dy whole power n minus 1 into du by dy whole power 1. Anyways, if I multiply these two, this minus 1 and plus 1 will get cancelled and finally I will get the same equation, right? So these two are same equation. And now see, this tau is in y-axis and du by dy is in x-axis. So this is the remaining term, right? So if I compare these two, tau is there, du by dy is there, du by dy is there, and in place of viscosity, I am having this total term, and I am going to take this total term as apparent viscosity. I will call this as apparent viscosity. Okay, so this total term is apparent viscosity. Now I can write tau is equal to mu apparent into du by dy, right? So this is my tau value. This is my tau for a dilatant fluid where mu apparent is what? Where mu apparent is equal to a into du by dy whole power n minus 1, right? So where mu apparent is a into du by dy whole power n minus 1. Now we are coming for a very important conclusion. See, mu apparent is equal to a into du by dy whole power n minus 1, and I know that for a dilatant fluid, n is greater than 1. If n is greater than 1, I can write n minus 1 is greater than 0, right? If n is greater than 1, then n minus 1 will be greater than 0, which means this n minus 1 is greater than 0. It is a positive value, right? Now say if du by dy increases, okay, n is positive, right? N is positive. If du by dy increases, since n is positive, if du by dy increases, this mu apparent value also increases, right? Since n is positive, this n is positive, so n minus 1 is also positive. Since n is greater than 1, n minus 1 is greater than 0. So du by dy as n increases, n minus 1 is positive, since n minus 1 is positive, this du by dy increases, then this mu apparent will also increase. It's very simple logic, right? Right hand side increases, left hand side will also get increased because this is having positive power. Now answer me. This du by dy is nothing but what? d theta by dt. So d theta by dt increases, du by dy, d theta by dt or du by di, both are same. We already discussed. Just go back to the initial video which we discussed. Du by dy is equal to d theta by dt. So if this increases means indirectly means that d theta by dt increases. So this is nothing but rate of shear strain or rate of angular deformation. This is nothing but velocity gradient. Now I will define what is dilatant fluid. Dilatant fluids are the fluid in which if rate of shear strain increases, if I increase the rate of shear strain, then its apparent viscosity will increase. Okay. Simply, I can give you some examples so that you will understand it in a much clearer manner. Take an example of rice starch. Okay, I guess everyone knows this. Rice starch is nothing but the white color liquid which you will get, after cooking the rice. Once if you cook the rice, you will be getting one white color liquid, right? Generally. Finally, after cooking the rice, you will be having two products. One will be rice, the cooked rice. Another one will be white color liquid. And that white color liquid is nothing but this rice starch. Now what you do, take that white color liquid in a small container, start to stir it. Okay, start agitating it, keep on stirring it. So if you keep on stirring it, what will happen to that? What will happen to that liquid? It will start to become thick, right? It will start to become thick. So what you are doing? I am stirring it, which indirectly means that I am increasing the deformation rate. I am increasing the deformation rate. Since deformation rate is increasing, viscosity is getting increased, apparent viscosity is getting increased, so the fluid is becoming thick. Okay, so it's very natural thing. Take that rice starch, start stirring it. Stirring indirectly means that you are increasing the rate of shear strain, and if you increase the rate of shear strain or rate of angular deformation, if you increase the deformation, then it results in increase in apparent viscosity. That is what we discussed in dilatant fluid. As rate of shear strain increases, apparent viscosity increases. So as I keep on stirring it, apparent viscosity increases. Sorry, as I keep on stirring it, shear strain increases and apparent viscosity increases, and this results in thickening of that fluid. So I will call this as shear thickening fluid. Very interesting concept, right? So if I keep on increasing this d theta by dt, the value of mu apparent is also getting increased. So because of that, the fluid is becoming thick, and hence I will call that as shear thickening fluid, and these types of fluid are nothing but dilatant fluid. Just go back and recollect what we discussed in case of Newtonian fluid. In Newtonian fluid, mu value is completely independent of du by dy. Just go back to the video which we already discussed. That time I clearly said mu is independent of du by dy, or mu is independent of d theta by dt. Even whatever I do, the mu value will remain constant even if I change this du by dy or d theta by dt. But in this case, as du by dy or d theta by dt increases, mu apparent is also increasing. In Newtonian fluid, as d theta by dt increases, mu will be constant only. So if mu is constant, which indirectly means that slope is constant. But in this case, what happened? This here the slope is apparent viscosity, right? Here the slope is not viscosity, here slope is apparent viscosity. So if d theta by dt increases, the slope value is also getting increased. But in case of Newtonian fluid, even d theta by theta increase also, that slope value, mu value, m value will be constant. Okay, this is the final outcome which I got, right, from dilatant fluid. If n is greater than 1 and b is equal to 0, tau will be equal to mu apparent into du by dy, where mu apparent is a into du by dy whole power n minus 1. And since n is greater than 1, n minus 1 will be greater than 0, so n is equal to positive, n will be positive. So since these terms, or n minus 1 is positive, n minus 1 is positive. Since n minus 1 is positive, this term is positive, so du by dy increases, mu apparent will increase. So that is what I get, du by dy or d theta by dt increases, mu apparent will increase. So if I want to plot it, so what is the definition here? If I increase, dilatant fluids are the fluid where if I increase the rate of deformation, it will result in increase in the apparent viscosity. Now if I plot it like this, tau as y and this as x, so if I plot tau in y axis and du by dy or d theta by dt, both are same in x axis. Now du by dy increases, tau is going to, du by dy increases, mu apparent is going to increase, and I know that this mu apparent is what? Mu apparent is nothing but my slope value. So if du by dy increase, so in this direction, in the positive direction, du by dy increases or d theta by dt increases, so the slope value should also increase. So slope increases means the curve will be something like this. So initially the slope was less, so this is my slope, so this is theta 1, and then the slope is keep on, initially this is my slope theta 1, now the slope is increasing, this is theta 2, and now the slope is further increasing, which is theta 3. So here theta value increases, nothing but slope value increases, right? And now about the slope, if you are not very clear about the slope, just go back and see the slope video which we already did in basic video lectures. Okay, just go and see the basic video lecture where I clearly mention what is slope, what is increasing, what is decreasing, and everything, right? So here as du by dy increases, the slope value increases, so the slope value will be keep on increasing, and this corresponds to dilatant. This corresponds to dilatant fluid. So we already seen we already seen Newtonian fluid where the slope value will be constant, it won't vary with respect to du by dy, but here slope value will be keep on increases as dilatant fluid because as the mu apparent value is keep on increasing. Now we will go for the next type of fluid. Next is pseudo plastic fluid, next type of non-Newtonian fluid. Here in case of pseudo plastic fluid, n is less than 1 and b is equal to 0, okay. Remaining thing are same whatever we did in case of dilatant fluid only changes here n is less than 1. So I can write the same equation in this like whatever we did in the last case, same type of derivation. So I will get the same equation and mu apparent is equal to a into du by dy whole power n minus 1. But now here n value is less than 1 which implies n minus 1 is less than 0. So this is very important. See, n minus 1 is becoming negative. Oh my god, n minus 1 is negative, which means this total value will be negative, right? For example, I will take n value is 0.5, okay, n is 0.5. Then what happened to mu apparent? For example, I am taking mu apparent is equal to a into du by dy whole power 0.5 minus 1 will be minus 0.5, which is equal to a by du by dy whole power 0.5, right, minus 0.5. So I can bring it to the denominator, it will become plus. Now answer me, if du by dy or else d theta by dt both are same, if du by dy or d theta by dt increases, what happens to mu apparent? Du by dy, if this increases, now it is in the denominator, if this increases, mu apparent decreases, right? So if du by dy increases, the apparent viscosity decreases. So here apparent viscosity decreases. So as du by dy or d theta by dt increases, apparent viscosity is decreasing. So here this type of fluid is called as shear thinning fluid. Let me take an example. Let us take an example. Take an example of blood, milk, etc. Take blood. Put a drop of blood in your hand. Initially when you are seeing it, it seems to be very thick, like it will be very thick. But once if you touch it, you can easily feel that it is moving very smoothly, right? There won't be any resistance, which indirectly means what actually you are doing. I am applying some force, which means I am deforming it. I am increasing the rate of deformation. Since the rate of deformation is increasing, the apparent viscosity decreases. So initially it will be thick, initially the viscosity will be more, but once if you apply the deformation, the viscosity decreases and hence you are feeling the blood is moving very smoothly. Same applicable for milk also. You can take a drop of milk and if you visualize, if you see it, you will be feeling like it is very thick, but once if you touch it, it will move very smoothly because the viscosity is decreasing as du by dt or as d theta by dt increases. Okay, so what can I say about the definition here? Here, a fluid is said to be pseudoplastic fluid if the rate of change of shear strain or rate of change of angular deformation increases, its apparent viscosity will decrease. Now the same story here, if I want to take this tau in y-axis and du by dy in x-axis, then if I plot it like this, tau du by dy or d theta by dt, both are same, d theta by dt. If I plot it like this, and this mu apparent is my slope, right? So now what is happening? If d theta by dt increases, my slope value is decreasing. So in the direction of positive d theta by dt, in this direction du by dy is increasing. So mu apparent will decrease, which means slope decreases, right? So in this direction d theta by dt increasing, so mu apparent will decrease, so slope value will decrease. So my curve will look something like, initially slope value will be more and then it will be keep on reducing. So initially the slope is very high and then it will keep on reducing and it is reaching lesser value. So here slope decreases, right? So as we keep on moving, the slope value is becoming less. We know that slope is nothing but representation of verticalness, right? So here if I draw a tangent, it will be like this, and if I draw a tangent, it will be like this, and if I draw a tangent, it will be like this, and here it will be like this. So you can see the verticalness of the tangent is keep on decreasing, nothing but the theta value is keep on decreasing. Okay. Next fluid, next type of non-Newtonian fluid is Bingham plastic fluid. So in Bingham plastic fluid, the condition is like B is not equal to 0 and N will be equal to 1. So what happens to tau? Tau is equal to A into du by dy whole power N, where N is 1 plus B, right? Now same thing, same concept. If I take tau in y and this du by dy in x, right? So how does it looks? Y is equal to mx plus c, right? So m and this is c, where m is what? Where m is nothing but slope and c is nothing but y-intercept, right? Simply our straight line equation, right? So m is the slope, which is a, and c is the y-intercept, which is nothing but b. Now let me first draw the curve. From that I could explain you very important or very interesting thing. So y-intercept is b, okay, y-intercept b. Let me take y is tau and this is du by dy. Let me take some value, this is b, okay, and I know that it is the equation of a straight line. So y-intercept is b, and after that the straight line will be something like this, and this represents tau is equal to a into du by dy plus b, right? So this is in y axis, this is in x axis, so y is equal to mx plus c equation, and this line represents Bingham plastic, that we clearly know. This represents Bingham plastic, that is fine. But now what actually it means? Now come on, let me give an example. See, let me take an example of a toothpaste or any gel, okay, or any cream or something like that. So let me take toothpaste, and now what I am doing is one end, at the end of the toothpaste I am applying some force, nothing but I am applying a shear force, right? I am applying shear force on the end of the toothpaste. If I apply shear force, initially what will happen? Slowly I am applying shear force, I am applying a force, very less force. The toothpaste will come out, like on the head of the paste will come out, but once if I remove it, it will go back again, right? Again I am applying some force, it is coming out, and once if I remove again, it is going back. So what actually it is doing, I am applying some shear force, the toothpaste is flowing, the paste is flowing, but once if I remove the shear force, it is coming back to its original position itself, right? So I am applying a force, it is flowing, and once if I remove, it is coming back to its original position itself. So what type of behavior it is? It is a solid behavior, right? It is like a solid. I am applying force, it is deforming, and again if I remove it, again it is coming back to its position. It is nothing but a behavior of solid. So it is a solid behavior. But now what happens? I am keep on applying force, and once the force reaches some value, it is flowing outside. Then I will take it out, and then I can brush. Okay. So I am applying. Once it reaches some value, it is flowing, and now even if I remove also, it won't go. It won't flow back again. Right. Now see. That value until which there won't be any deformation, this du by dy or d theta by dt, right? D theta by dt is nothing but the deformation. So I am keep on applying shear, until it reaches this point. There is no flow, there is no deformation, only shear stress value is keep on increasing and it reaches this point, but there is no flow, there is no deformation, and after that it start to flow. So what is happening? I am applying shear force until it reaches this B point. It is behaving like a solid. I am applying a force, and again if I remove it is coming back. I am applying a force, again if I remove it is coming back. So until this point it is behaving like a solid, and once it reaches this point it started to flow. It is actually normally behaving like a fluid itself. So this type of fluid where until some point it is going to behave like a solid, and after that it is going to behave like a fluid, it is called as Bingham plastic fluid, and this stress is yield stress. So once it crosses this yield stress value, it will start to behave like a fluid. Until that it will behave like a solid only. So let me plot all the things which we discussed it now, all the fluid in a single graph. So if I plot tau versus du by dy, okay, or d theta by dt, both are same, or d theta by dt. If I plot it in a single graph, first is Newtonian fluid, right? So this is my Newtonian fluid where viscosity is not going to change with respect to deformation. Next is dilatant fluid, right? So next is dilatant fluid. Let me write it here. So Newtonian fluid where n value is equal to 1 and b value is equal to 0. Next is dilatant fluid. So this is my dilatant fluid. So here in case of dilatant fluid, the apparent viscosity increases as deformation increases, so slope value is increasing. And now next is pseudo plastic. So in case of pseudo plastic, the apparent viscosity decreases as deformation, rate of deformation increases, so slope value is decreasing. And next, finally, we discussed about Bingham plastic, which is nothing but Bingham plastic or ideal plastic. So Bingham plastic fluid. So here this is B, and for this n value is equal to 1 and b value is not equal to 0. And now these are the different types of fluid which we seen it now. Now we have another two more classification. First is ideal fluid. All these fluids are real fluid, okay, all this fluid has viscosity, okay, it has some component of viscosity. But ideal fluid are something where viscosity will be 0, that is there is no viscosity. Assumption of ideal fluid, assuming that there is no viscosity, there is no surface tension. Sigma implies surface tension here. We will discuss about surface tension later. There is no viscosity, there is no surface tension, and finally we are going to treat that it is incompressible, which means density will be constant. So ideal fluid is an hypothetical fluid. There is no such fluid, there is no such thing called as ideal fluid in reality. So it's an hypothetical way where I am considering there is no viscosity, no surface tension, and the fluid is incompressible, density is constant. Now come on, let me plot it in this graph. Where that ideal fluid will come? d by dy and tau. If mu is not there, then there is nothing to resist, right? So there won't be any, there is no requirement for any shear stress to cause the deformation. So it will be exactly horizontal line itself. This horizontal line represents ideal fluid, okay. So where viscosity is not there, there is no viscosity, so there will be continuous deformation even without applying of shear stress. Even I don't want to apply small shear stress also, but there will be continuous deformation. So shear stress will also be 0 in case of ideal fluid. Since mu is 0, shear stress will also be 0, so it represents this curve. So tau is equal to 0. Now come for another case. It's not a fluid, it's a solid, ideal solid. In case of engineering mechanics, we will discuss about this ideal solid, or also it is rigid body. Okay, rigid body in the sense deformation won't be there, there won't be any deformation, deformation is equal to 0. So in this graph deformation is nothing but x-axis, so x will be always 0, deformation will be always 0, which indirectly means that this particular y-axis, so this corresponds to ideal solid, okay. So ideal solid where the deformation is 0 and ideal fluid where the shear stress will be 0, there is no resistance against the shear stress. So at now whatever we seen, Newtonian fluid, non-Newtonian fluid, real fluid, or whatever fluid we seen at now, or time independent fluid. Time independent fluid means viscosity is not a function of time. With respect to time, viscosity is not going to change, then I will call it as time independent fluid. If it is a time dependent fluid, then based on time this viscosity value might change. So there are two classifications. First one is First one is viscosity increases. So viscosity will increase as time increases, and those type of fluid are called as rheopectic fluid. And viscosity decreases as time increases, and those types of fluid are called as thixotropic fluid. So rheopectic and thixotropic fluid. Now in case of rheopectic fluid, as time increases, viscosity is increasing, right? So what could be some example which I could take? It's very simple, right? Some examples. Glues, fevicols, right? These are some examples where it will, if I just keep that glue and fevicol for longer time, its viscosity obviously going to increase, right? So viscosity increases as time increases. And for thixotropic, I can give examples such as lipstick and paint. So here where viscosity will decrease if time increases.